The Milky Way is a barred spiral galaxy, one of hundreds of billions scattered across the observable universe. But before we continue, please make sure to subscribe and leave like for more sleepy science videos. A galaxy, in its simplest definition, is a vast gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. These components form complex structures, from dense central bulges to sprawling spiral arms. The Milky Way's dimensions are immense. It stretches about 100,000 light-years across and contains an estimated 100 to 400 billion stars, along with countless planets, nebulae, and star clusters. Structurally, the Milky Way has several key regions. At its center lies the galactic bulge, hosting a supermassive black hole named Sagittarius A star. Surrounding this core is a thin, rotating disk of stars and gas, organized into multiple spiral arms where new stars are actively forming. The disk is enveloped by a spherical halo containing ancient stars, globular clusters, and the elusive dark matter that shapes the galaxy's gravitational field. Within the vast cosmic tapestry, the Milky Way is considered a typical large spiral galaxy, though it plays a central role for us as the home of the solar system. It belongs to the local group of galaxies, where its gravitational interactions and future merger with the Andromeda Galaxy define its long-term destiny. Roughly 13.8 billion years ago, the universe began with the Big Bang, an immense expansion from an extremely hot, dense state. In the very first fractions of a second, the cosmos was a sea of fundamental particles, quarks, gluons, electrons, photons, and neutrinos, all colliding at unimaginable energies. As the universe expanded, it cooled rapidly, allowing quarks to combine into protons and neutrons. Within the first few minutes, conditions became suitable for nuclear fusion in a process known as Big Bang nucleosynthesis. This short but crucial phase produced the lightest elements, mostly hydrogen nuclei, protons, helium, 4 nuclei, and trace amounts of deuterium, helium-3, and lithium-7. Heavier elements did not form at this stage because the universe cooled too quickly for prolonged nuclear reactions, and the density was too low to sustain them. These primordial elements were not yet organized into stars or galaxies. Instead, they existed in a nearly uniform plasma of charged particles and photons. For about 380,000 years, the universe remained in this ionized state. During this era, called the photon-baryon fluid phase, light could not travel freely because photons were constantly scattered by free electrons in the plasma. The density of matter was astonishingly high compared to today, millions of times denser than the current intergalactic medium, and the temperature was on the order of several thousand Kelvin, comparable to the surface of a star. Eventually, as expansion continued, the temperature dropped below roughly 3,000 K. This cooling allowed protons and electrons to combine into neutral hydrogen atoms, a process called recombination. With electrons now bound to nuclei, photons could travel freely across space, releasing the cosmic microwave background radiation we can still detect today. This radiation preserves a snapshot of the universe at that moment, a nearly uniform glow with slight temperature fluctuations that trace the seeds of future large-scale structures. The intergalactic medium, IgM, after recombination was far from lifeless. Although largely uniform, it carried small density variations, tiny over and under densities that had been imprinted during the universe's inflationary phase. Gravity acted more strongly in slightly denser regions, pulling in more matter and initiating the earliest stages of structure formation. In this period, the composition of the IgM was remarkably simple, about 75% hydrogen and 25% helium by mass, with minute traces of lithium. These ratios have remained essentially unchanged in regions of the universe that have not undergone stellar processing. At this stage, dust, in the modern sense of solid microscopic grains, did not yet exist. The term primordial gas dust cloud is more applicable to later phases, after the first stars formed and expelled heavier elements into the surrounding medium. In the truly primordial epoch, the dust component was absent because dust grains require metals like carbon, silicon, and oxygen to form. Thus, the early clouds were pure gas, made only of hydrogen, helium, and a sprinkling of lithium atoms. The density of the IgM at this time was still vastly greater than today's near vacuum. Modern intergalactic space has an average density of only about 1 hydrogen atom per cubic meter, but in the hundreds of millions of years following recombination, this density was millions of times higher. The temperature, while much cooler than during the plasma era, was still sufficient to keep the gas from condensing immediately. Over the next few 100 million years, cosmic expansion continued to stretch and cool the gas, lowering its temperature to just a few tens of Kelvin in the coldest regions. It was during this prolonged dark age of the universe, after the release of the cosmic microwave background but before the first stars, that gravity slowly amplified the initial density fluctuations. The invisible scaffolding of dark matter halos began to form, pulling in the primordial gas. These halos served as gravitational wells into which hydrogen and helium could fall, gradually forming denser regions. In the densest pockets, gravitational collapse accelerated, and temperatures rose again as gas was compressed. This set the stage for the ignition of the first stars, marking the end of the cosmic dark ages. From the perspective of the Milky Way's history, the primordial gas from which it eventually formed was part of this early intergalactic medium. It did not collapse directly into a galaxy at once. Rather, it was drawn into a web of dark matter structures that merged over time. The gas destined to become the Milky Way likely passed through several intermediate stages, from diffuse IgM to clumps within protogalactic clouds to dense star-forming regions. But the initial composition, almost pure hydrogen and helium, with no metals, dictated that the very first generation of stars, population 3 stars, would be massive, hot, and short-lived. Temperature played a critical role in this evolution. Gas in the early universe could not cool efficiently because it lacked heavy elements, which are essential for radiating heat away in molecular form. The only cooling pathways available were through molecular hydrogen, H2, which formed in small amounts in dense regions. Without efficient cooling, the first collapsing gas clouds tended to fragment into large clumps, producing stars dozens or even hundreds of times the mass of the Sun. These stars burned through their fuel rapidly and exploded as supernovae, ejecting newly forged heavy elements into the surrounding gas. Only after this enrichment phase could true dust grains form, allowing subsequent generations of stars to be smaller and longer-lived. The temperature evolution of the IgM thus followed a complex curve, from millions of Kelvin immediately after the Big Bang, to a few thousand Kelvin at recombination, to under 100 Kelvin during the Dark Ages, and then rising locally again in collapsing halos. Over time, as more stars formed, ultraviolet radiation from these first luminous objects began to reionize the neutral hydrogen in the IgM, a global phase transition known as cosmic reionization. This event occurred roughly 500 million to 1 billion years after the Big Bang, restoring the IgM to an ionized state in most regions, much like the earlier plasma era, but at far lower densities. In summary, The primordial gas dust cloud that would one day give rise to the Milky Way had its origins in the earliest minutes of cosmic history. Its hydrogen and helium were born in the furnace of Big Bang nucleosynthesis, its lithium a rare byproduct of the same process. For hundreds of millions of years, this material drifted through an expanding, cooling universe, shaped subtly by gravitational instabilities seeded in the first instance of time. Though invisible to the naked eye, it was the raw material from which all stars, planets, and life would ultimately emerge. Only after the first stars lit up and seeded the cosmos with heavy elements could the familiar cycle of gas, dust, and star formation begin, the very cycle that, billions of years later, would produce the spiral galaxy we now call home. After the era of recombination and the long stretch of cosmic dark ages, the universe remained largely uniform in composition but not perfectly smooth in density. Embedded within the cosmic fabric were tiny irregularities, minute fluctuations in matter density left over from quantum variations during the earliest moments after the Big Bang, amplified by cosmic inflation. These slight overdensities, visible today as faint variations in the cosmic microwave background temperature, were the seeds from which galaxies, including the Milky Way, would eventually grow. In regions where matter was marginally denser than average, gravity began to assert its influence more strongly. Over hundreds of millions of years, the extra pull in these regions slowed their local expansion relative to the rest of the universe. While the universe as a whole continued to stretch outward, these pockets of overdensity gradually decoupled from the general expansion and began to contract under their own gravity. One of these regions would eventually become the birth site of the Milky Way. At this stage, two key components shaped the process: ordinary, baryonic matter, which made up the gas of hydrogen and helium, and dark matter, the invisible but dominant mass component. Dark matter had been gathering into clumps, called halos, long before baryonic matter could follow. Unlike gas, dark matter does not interact with light or other forms of electromagnetic radiation. It only responds to gravity. Because it could not dissipate energy through radiation, dark matter did not collapse into disks or clouds the way gas does, but instead formed extended, roughly spherical halos. These halos acted as gravitational wells, pulling in surrounding baryonic gas. The influence of dark matter on matter concentration was decisive. Without dark matter, the tiny density fluctuations in the early universe would have been erased by the pressure of photons and the random motions of gas. Dark matter, being unaffected by radiation pressure, could begin clustering even before recombination, providing a kind of gravitational scaffolding for ordinary matter to fall into. As the baryonic gas cooled after recombination, it was able to sink into the potential wells created by dark matter halos. In the case of the protogalactic region that would form the Milky Way, the process unfolded gradually. Over time, smaller dark matter halos merged into larger structures in a hierarchical fashion. This merging process deepened the gravitational potential, attracting ever more gas. By roughly a few hundred million years after the Big Bang, the overdense region contained both a substantial dark matter halo and an increasing concentration of hydrogen and helium gas at its center. The gravitational collapse of the baryonic matter followed a specific pattern. Initially, the gas was nearly uniform, but as it fell inward, it encountered shocks and compressions that heated it to thousands of Kelvin. For collapse to continue, the gas had to lose this heat. Without efficient cooling, the pressure from hot gas would counteract gravity and halt the process. In the earliest stages, molecular hydrogen, H2, was the only significant coolant available, allowing the gas to radiate away some of its heat in the infrared spectrum. Though inefficient compared to cooling by heavy elements, it was sufficient to allow further contraction in localized dense regions. As collapse proceeded, the overdense region's geometry began to change. While dark matter maintained a roughly spherical distribution, the gas, unlike dark matter, could lose energy through radiation and settle into a more compact configuration. Conservation of angular momentum played a crucial role here. Even a small initial spin in the collapsing region was amplified as the gas contracted, leading to rotational flattening. This marked the early stages of the protogalactic cloud, a vast, rotating mass of gas embedded within a dark matter halo, already showing hints of the flattened structure that would later evolve into a galactic disk. The formation of the protogalactic cloud was not a perfectly smooth process. The gravitational potential of the dark matter halo was irregular due to the clumpy nature of the matter distribution, and this caused streams of gas to fall in along preferred directions, often along filaments of the large-scale cosmic web. These inflows brought fresh material from the intergalactic medium and sometimes collided with existing gas clouds, triggering turbulence and compressions that accelerated local collapse. At the same time, smaller satellite halos, each with their own gas content, were merging with the main protogalactic halo. These mergers were chaotic events, sometimes inducing shocks that heated the gas and temporarily slowed star formation, but also deepening the gravitational potential and increasing the mass concentration. In a sense, the protogalactic cloud was not a single, isolated sphere collapsing inward, but rather a dynamic and growing structure assembled from many smaller components over time. Dark matter's role continued to be critical throughout. Because dark matter composed the bulk of the mass, it determined the depth and shape of the gravitational well. Even when gas was heated and driven outward by shocks, the gravitational pull of the dark matter halo tended to retain most of it, allowing the protogalactic region to recover and continue its growth. Moreover, the velocity dispersion of dark matter particles set the overall scale of the halo, influencing how large the protogalactic cloud could become before stabilizing. By the time the protogalactic cloud reached a mass of perhaps tens of billions of solar masses, its central gas density had grown high enough to initiate the formation of the first stars within it. These early stars, belonging to the so-called Population 3, were massive, short-lived, and extremely luminous. They formed in the densest knots of gas within the protogalactic cloud, quickly altering their surroundings with intense ultraviolet radiation and supernova explosions. These energetic events both enriched the gas with heavier elements and stirred it, redistributing matter within the cloud. The enrichment of the gas was a turning point. Once heavier elements were present, cooling became far more efficient because atoms like carbon and oxygen, as well as dust grains, could radiate heat away effectively. This allowed gas to collapse into smaller clumps, giving rise to a wider range of star masses, including long-lived stars like the Sun. Over time, repeated cycles of star formation and feedback began shaping the internal structure of the protogalactic cloud, gradually leading toward the familiar components of a mature galaxy: a bulge, a disk, and a halo of old stars. Still, at this stage, the Milky Way was not yet the grand spiral galaxy we see today. The protogalactic cloud was more chaotic and irregular, its rotation not yet organized into well-defined spiral arms. It was a transitional structure, massive and gravitationally bound, with a dense central region, but still actively accreting material and undergoing frequent mergers. The dark matter halo surrounding it extended far beyond the visible gas and stars, defining the ultimate scale of the galaxy to be. In essence, the birth of the local overdensity region and its evolution into a protogalactic cloud was the outcome of billions of years of gravitational amplification, hierarchical merging, and the interplay between dark and baryonic matter. The small density fluctuation that began as an almost imperceptible difference in the early universe became, through the relentless pull of gravity, a massive, rotating reservoir of gas, primed for the star formation that would ultimately give rise to the Milky Way. Without the silent but dominant presence of dark matter, this process would not have proceeded quickly or strongly enough to produce the galaxy within the age of the universe. The protogalactic cloud was both a product of cosmic structure formation and the starting point for the intricate stellar architecture we see today. In the earliest epochs of the universe, after the gravitational collapse of primordial gas within the first dark matter halos, conditions were set for the birth of the very first stars. These stars, known as Population 3, were unlike any that exist today. They formed from gas composed almost entirely of hydrogen and helium, with only trace amounts of lithium, and crucially, no heavier elements, what astronomers call metals. The absence of these metals fundamentally altered the physics of star formation, shaping the masses, lifespans, and eventual fates of these first luminous objects. In modern star-forming regions, heavy elements such as carbon, oxygen, and silicon, along with dust grains, play an essential role in cooling gas clouds. They radiate heat away efficiently, allowing clouds to fragment into smaller pieces, which then collapse into stars of modest mass. But in the metal-free universe, cooling options were extremely limited. The primary coolant available was molecular hydrogen, H2, which could radiate heat away through rotational and vibrational transitions in the infrared, but far less effectively than metals or dust. This inefficiency meant that collapsing gas clouds remained relatively warm, resisting fragmentation into many small clumps. Instead, they tended to form a few massive condensations. Simulations of these conditions suggest that Population 3 stars were typically much more massive than most stars today, often in the range of tens to hundreds of times the mass of the Sun. The larger the mass, the stronger the gravitational pull, which compressed the gas even further and ignited nuclear fusion at extremely high temperatures and luminosities. These stars shone with an intensity thousands to millions of times greater than the Sun, and their surface temperatures often exceeded 50,000 Kelvin, bathing their surroundings in intense ultraviolet radiation. The high mass of Population 3 stars had two important consequences for their evolution. First, they burned through their nuclear fuel extremely rapidly. While a star like the Sun has a main sequence lifetime of about 10 billion years, a 100 solar mass Population 3 star might exhaust its hydrogen in just a few million years. Second, their cores reached conditions capable of synthesizing heavier elements far more quickly than lower mass stars could. During their short lives, nuclear fusion in their cores transformed hydrogen into helium, and then through successive fusion stages produced carbon, oxygen, and other elements up to iron in the most massive cases. Because these stars lived fast and died young, they profoundly altered their environments almost immediately after forming. Even before their explosive deaths, their ultraviolet light began to ionize the surrounding hydrogen gas, creating expanding bubbles of ionized plasma called H2 regions. This radiation contributed to the gradual reionization of the intergalactic medium, a major phase transition in cosmic history. The most dramatic impact, however, came at the end of their lifespans. The most massive Population 3 stars exploded as parent stability supernovae, an especially powerful type of stellar explosion. In such stars, the core temperatures became so high that gamma-ray photons were converted into electron-positron pairs, reducing radiation pressure and causing a sudden partial collapse. This collapse ignited runaway fusion reactions, releasing enough energy to completely disrupt the star, leaving no remnant behind. In the process, enormous quantities of heavy elements were expelled into space. Less massive but still large population 3 stars may have ended their lives as core collapse supernovae, producing neutron stars or black holes as remnants. These explosions also injected newly forged elements into the surrounding gas, though typically in smaller amounts than parent stability events. Across both cases, the result was the same in broad terms. Regions of pristine hydrogen and helium were enriched with the first significant amounts of carbon, oxygen, magnesium, silicon, and other metals. This enrichment marked a turning point in the chemical evolution of the universe. With even small traces of heavy elements now present in the interstellar medium, gas clouds could cool much more efficiently. Cooling allowed them to fragment into smaller clumps, leading to the formation of lower-mass stars, the first examples of population 2 stars, some of which have survived to the present day. Thus, the brief lives of population 3 stars set in motion a chain of events that would change the character of star formation forever. The metals dispersed by these first supernovae were also the raw materials for future planetary systems. Carbon and oxygen would form the basis for organic chemistry. Silicon and iron would form the cores and mantles of rocky planets. Although the Milky Way would not exist for hundreds of millions of years after the first population 3 stars died, the seeds of its eventual composition were planted in this early enrichment era. It is worth noting that not all population 3 stars enriched their surroundings equally. The most massive ones that collapsed directly into black holes without a supernova contributed little to the chemical buildup, but they may have seeded the growth of supermassive black holes in galactic centers. The diversity of fates among these first stars created a patchwork of enriched and still pristine regions in the young universe. This uneven distribution influenced where the next waves of star formation could occur and where conditions would remain metal-free for longer. As more halos formed and merged, the products of multiple population 3 supernovae mixed together, raising the average metallicity of gas across larger volumes. Over time, metal-free star formation became rarer, and the era of true population 3 stars gradually came to a close. However, the exact timeline of this transition is still a subject of active research. Astronomers continue to search for indirect evidence of population 3 stars by studying the chemical composition of extremely metal-poor stars in the Milky Way's halo, as these ancient survivors may have formed from gas enriched by only one or a few early supernovae. In the evolutionary story of the Milky Way, the population 3 phase was the prologue, a brief but essential chapter. The protogalactic cloud that would one day form our galaxy was influenced by the enrichment patterns established in earlier structures. By the time the Milky Way's main halo was assembling, much of its incoming gas already contained traces of metals from long-dead population 3 stars. This early chemical heritage shaped the properties of the first stars born within our galaxy's boundaries and determined how quickly complex structures like spiral arms and planetary systems could emerge. From a cosmic perspective, the first stars were both creators and destroyers. They forged the universe's first heavy elements in their cores, but their intense radiation and violent deaths also disrupted and reshaped their surroundings. Without them, the universe would have remained chemically simple, and the path toward galaxies rich in diversity, including the Milky Way, would have been impossible. Their legacy is written not in surviving examples, for none are known to still exist, but in the atoms we find all around us today, in the oxygen we breathe, the carbon in our cells, and the iron in our blood. These elements, so fundamental to life and planetary structure, had their origins in the brief, brilliant lives of population 3 stars, whose existence transformed a dark and simple cosmos into a complex and evolving universe. As the protogalactic cloud destined to become the Milky Way continued to grow in mass through the accretion of gas and the merging of smaller halos, its evolution began to shift from a largely chaotic collapse into a more ordered, rotationally influenced structure. The presence of angular momentum, even if initially small, was inevitable. No collapsing gas cloud in the universe is perfectly symmetrical or stationary. Random motions, gravitational interactions with surrounding structures, and tidal torques from neighboring protogalaxies all impart some degree of spin. Over cosmic time, as the gas contracted, this spin was amplified, driving the gradual transformation of a roughly spheroidal cloud into a flattened, rotating disk. The physics of this transformation is rooted in the conservation of angular momentum. When a large volume of gas collapses under gravity, its moment of inertia decreases as it becomes more compact. Since angular momentum, the product of rotational velocity and moment of inertia, must be conserved in the absence of external torque, the rotational speed of the collapsing cloud increases. The faster the spin, the greater the centrifugal force acting perpendicular to the axis of rotation. This force does not halt collapse along the rotation axis, but it does resist contraction in the plane of rotation. The result is a progressive flattening of the cloud into a disk-like form. Initially, this disk was far from the neat, well-defined spiral pattern we see in the Milky Way today. It was turbulent, clumpy, and still in the process of accumulating mass from multiple directions. Streams of gas continued to flow in along the filaments of the cosmic web, delivering fresh material to the outer regions. These inflows often arrived with different angular momentum orientations, creating asymmetries and instabilities in the developing structure. Collisions between infalling gas clouds generated shocks that dissipated energy and helped the gas settle into the main rotational plane of the protogalaxy. While the dark matter halo remained largely spherical, providing the gravitational framework, the baryonic gas could radiate away heat through atomic and, increasingly, metal line cooling. This ability to lose thermal energy allowed it to collapse further than the dark matter could, concentrating in the central regions where the rotational dynamics dominated. Over time, the gas distribution became increasingly flattened, with the densest concentrations forming toward the middle, where the seeds of the galactic bulge were already present. The flattening process was not instantaneous. Early in the collapse, the protogalactic cloud still contained significant vertical thickness, more like an oblate spheroid than a razor-thin disk. Turbulence, driven by ongoing mergers and supernova explosions from the first generations of stars, stirred the gas, resisting the formation of a smooth, stable disk. Yet each dissipative event, each shock, collision, and cooling episode, drained energy from the chaotic motions, allowing more material to settle into ordered rotation. One of the critical factors in disk formation was the gradual alignment of angular momentum. As infalling gas mixed and exchanged momentum through hydrodynamic interactions, a dominant rotation axis emerged. This process could take hundreds of millions of years, but as it progressed, more of the gas moved into near-circular orbits within a common plane. The resulting rotational support balanced gravity in the radial direction, preventing further collapse inward except where instabilities triggered star formation or where the mass density was high enough to overcome rotational support. By this stage, the protogalactic disk was taking on its first recognizable outlines. The central bulge region, fed by low angular momentum material, was more spherical and densely packed with stars and gas. Surrounding it, the rotating disk extended outward for tens of thousands of light years, though its outer edges were ill-defined and continually shifting as new material was accreted. The gas in the disk was not yet smoothly distributed. Rather, it was concentrated in large, irregular clumps where density was high enough to form new stars. Star formation in this early disk was vigorous, fueled by the abundant cold gas flowing inward. Many of the stars formed at this time would be considered population 2, older, metal-poor stars, but with higher metallicity than the pristine population 3 generation. These stars began to populate both the disk and the halo, with some flung into eccentric orbits by gravitational interactions. Meanwhile, massive star clusters formed in the densest regions, some of which would survive as ancient globular clusters still orbiting the Milky Way today. The influence of rotation on the evolving disk extended beyond just its flattening. Rotational dynamics also set the stage for the development of spiral structure. Though in this early epoch the arms were likely short-lived and irregular, appearing as transient density waves rather than the grand, symmetric spirals we observe in mature galaxies. These nascent arms acted as sites of enhanced star formation, where gas clouds were compressed and fragmented under the combined influence of gravity and shock waves. As the disk grew, it interacted with the surrounding halo and the infalling satellites. Minor mergers could thicken the disk temporarily, disturbing its structure, while major mergers had the potential to disrupt it entirely. The Milky Way's eventual survival as a disk galaxy indicates that, while mergers did occur during this time, they were not so violent or frequent as to destroy the disk's integrity. Instead, many of the accreted satellites contributed stars and gas to the halo, leaving the disk relatively intact to continue its evolution. An important aspect of this formative stage was the balance between cooling and heating processes. Gas cooling, from atomic transitions, molecular lines, and radiation from metals, worked to allow the disk to become thinner and more rotationally supported. Heating, on the other hand, came from supernova feedback, stellar winds, and gravitational interactions, which injected energy back into the gas, maintaining a certain degree of turbulence. The interplay between these effects determined the disk's thickness, star formation rate, and stability. By the end of this phase, the protogalactic disk had achieved a coherent, large-scale rotation, with the majority of its baryonic mass lying in a flattened structure embedded within the dark matter halo. Its bulge was already forming through the inward migration of dense clumps and the accumulation of low-angular momentum gas. The outer disk regions remained somewhat irregular, shaped by continuing accretion and localized bursts of star formation. This stage represented a major milestone in the Milky Way's evolution. The transition from a chaotic, roughly spherical gas cloud to an organized, rotating disk was the foundation upon which all later galactic structure would be built. Over the next billions of years, this disk would evolve into a more stable and refined form, develop lasting spiral arms, and nurture the environments in which planetary systems, and eventually life, could arise. But the fundamental geometry and rotational dynamics established in the proto-galactic phase would persist, defining the Milky Way's character as a disk galaxy for the remainder of its history. Following the settling of the proto-galactic cloud into a rotating disk, the Milky Way entered a transformative period known as the intense star formation epoch. This was a time when the galaxy's gas reservoirs were abundant, cold enough to collapse, and continuously replenished by inflows from the surrounding cosmic web. The conditions favored rapid and widespread star formation, far exceeding the pace observed in the Milky Way today. In this phase, the galaxy began to assemble many of the structural components and chemical characteristics that would define it for billions of years. The first and most striking effect of this starburst phase was the emergence of dense stellar regions across the young disk. Large clumps of cold molecular gas, triggered by gravitational instabilities and compressive shocks, collapsed to form massive star clusters. Among the most prominent of these were nuclear star clusters in the central regions of the galaxy, where gravitational potential was deepest and gas density highest. These central clusters formed rapidly, with stellar densities millions of times greater than in the solar neighborhood today. The nuclear cluster was not an isolated entity, but part of a broader buildup of the galactic bulge. Low angular momentum gas streaming toward the center fueled intense bursts of star formation, creating a dense, spheroidal population of stars with a broad range of ages and metallicities. Some of these early bulge stars still exist, their orbits and compositions preserving clues about the conditions of this formative era. In the disk itself, the high gas fraction, possibly 50% or more of the baryonic mass, led to the formation of massive star-forming clumps, some containing billions of solar masses of gas and stars. These clumps were hotbeds of stellar birth, producing both massive, short-lived stars and lower mass, longer-lived ones. Feedback from the massive stars, through ultraviolet radiation, stellar winds, and supernova explosions, helped regulate the star formation rate, preventing the gas from collapsing everywhere at once. This self-regulation maintained a dynamic equilibrium. Dense regions would ignite in a starburst, then be partially disrupted, allowing gas to disperse and later collapse again in new locations. The impact of massive stars on their surroundings went beyond regulating star formation. Through nucleosynthesis in their cores and subsequent supernova explosions, these stars enriched the interstellar medium, ISM, with heavier elements, the process astronomers call chemical enrichment. Carbon, oxygen, silicon, and iron were among the elements produced and dispersed during this time. Each generation of massive stars lived only a few million years before exploding, ensuring that the cycle of enrichment was rapid compared to cosmic timescales. Chemical enrichment had far-reaching effects. With each infusion of metals into the ISM, the cooling efficiency of the gas improved, allowing it to fragment into smaller clumps. This fragmentation enabled the formation of stars across a wider range of masses, including many low-mass stars capable of surviving for billions of years. Some of these low-mass stars born in this epoch are still present in the Milky Way today, serving as living fossils of the galaxy's early starburst period. The rapid buildup of metals also laid the groundwork for the eventual formation of planetary systems. Dust grains, which form from elements such as carbon, silicon, and iron, began to appear in the ISM. These grains played a dual role. They enhanced cooling by radiating away heat and provided the raw material for solid planetary cores in the protoplanetary disks around young stars. While planets would not form in large numbers until later, the chemical prerequisites were being put in place during this intense star-forming era. Star formation during this time was not evenly distributed across the disk. Large-scale gravitational instabilities and interactions with infalling satellite galaxies created asymmetric patterns of density, leading to the development of protospiral features and irregular arm-like structures. These features acted as density waves, compressing gas and triggering further star formation along their crests. Although these spiral patterns were likely transient and clumpy compared to the grand, symmetric spirals seen in the present-day Milky Way, they marked the beginning of the galaxy's spiral morphology. The central regions of the galaxy, the bulge and the inner disk, saw the most rapid enrichment, as they hosted the highest densities of massive stars and supernovae. The halo, in contrast, was enriched more slowly, as its stars formed in smaller, less gas-rich environments. Many of the stars in the halo were likely born in smaller satellite galaxies that merged with the Milky Way during this period, bringing in their own distinct chemical signatures. The mixture of these external contributions with the Milky Way's native enrichment history created the complex chemical diversity observed in halo stars today. Supernova-driven outflows were another defining feature of this epoch. The enormous energy released by thousands of supernovae in a short period could drive gas out of the disk and into the surrounding halo, creating a galactic fountain effect. Some of this gas cooled and fell back into the disk, bringing metals to regions far from their original sources, while some escaped entirely into intergalactic space, contributing to the enrichment of the cosmic environment. These outflows helped distribute metals more evenly across the galaxy and beyond, but they also temporarily reduced the gas available for star formation. The intense star formation epoch was therefore a delicate balance between gas consumption, replenishment, and dispersal. Inflows from the intergalactic medium and merging satellites kept the gas supply high, while star formation and feedback continually reshaped its distribution and properties. The net result was a galaxy that, over the course of several 100 million to a few billion years, transformed from a relatively primitive, metal-poor system into a chemically diverse and structurally complex young spiral galaxy. By the end of this phase, the Milky Way had already developed many of its defining features: a prominent central bulge with a dense nuclear star cluster, an extended but still thick disk populated by a mix of young and older stars, and a halo containing remnants of early mergers. The ISM was significantly enriched, with metallicity in the central regions approaching or surpassing 10% of the Sun's current value. This set the stage for a slower, more regulated mode of star formation in the subsequent billions of years. In the grand arc of the Milky Way's history, the intense star formation epoch was a time of extraordinary creativity and transformation. The galaxy grew rapidly in stellar mass, diversified its chemical composition, and laid the foundations for the stable, metal-rich environment in which later generations of stars, including the Sun, would form. Without this period of prolific star birth and enrichment, the Milky Way would not possess the complexity, structure, or capacity to host life-bearing planets that it does today. As the young Milky Way's proto-galactic disk matured during its intense star formation epoch, the processes at work in the galaxy's central regions began to diverge from those in the outer disk. The inner gravitational well, deepest at the very heart of the galaxy, exerted a powerful influence on the inflowing gas and stars. Over time, this led to the condensation of a dense, spheroidal stellar structure that we now recognize as the galactic bulge. The bulge's origins can be traced to the earliest phases of gas inflow toward the center. Not all of the material within the proto-galactic disk possessed the same amount of angular momentum. Gas with lower angular momentum was less able to maintain an extended orbit in the disk plane and therefore spiraled inward under the pull of gravity. This inward migration was accelerated by dynamical friction between massive clumps of gas and stars, as well as by the gravitational torques exerted by non-uniform features in the young disk, protospiral arms, bars, and irregular mass concentrations. As gas funneled toward the center, it accumulated in vast quantities, reaching densities far higher than those typical of the disk. The increased pressure and self-gravity of this central gas reservoir triggered intense bursts of star formation. Many of these newly formed stars were massive, short-lived, and highly luminous, contributing to the rapid chemical enrichment of the region. Their eventual supernova explosions injected heavy elements back into the surrounding medium, accelerating the metallicity increase of the central gas. The result was the emergence of a densely packed stellar population with a wide range of ages, but skewed toward the oldest stars in the galaxy. The most ancient stars in the bulge formed during this early, violent period of assembly, locking in the chemical fingerprints of the first few 100 million years of enrichment. Because the bulge experienced a much higher star formation rate than the outer disk, its metallicity rose quickly, creating an environment where even stars born relatively early could be as metal-rich as, or richer than, the Sun. Alongside the buildup of the bulge's stellar mass, another central structure began to take shape: the supermassive black hole, SMBH, at the galaxy's heart. The seeds of this black hole may have originated in one of two ways: either from the direct collapse of a massive gas cloud in the nucleus, or from the remnants of one or more extremely massive population 3 stars that had collapsed into black holes. In either scenario, the dense and gas-rich environment of the central bulge provided a ready supply of material for the black hole to accrete. As matter fell into the growing SMBH, gravitational energy was converted into radiation, producing an active galactic nucleus, AGN. In its most energetic phases, the Milky Way's central black hole may have rivaled the luminosity of a small galaxy, emitting powerful jets and winds that affected the surrounding bulge. This AGN feedback, along with the combined energy of countless supernovae, may have played a role in regulating star formation by heating or expelling gas from the innermost regions. The interplay between gas inflow, star formation, and black hole growth was complex and self-reinforcing. Gas inflows fed both star formation and SMBH accretion. Massive stars and the AGN, in turn, drove outflows that could limit further accretion. This feedback cycle likely occurred multiple times in bursts, producing alternating periods of rapid growth and relative quiescence in the bulge's history. Structurally, the bulge took on a three-dimensional, ellipsoidal shape, quite distinct from the thin, flat disks surrounding it. While some bulges in other galaxies form largely through mergers, evidence suggests that the Milky Way's bulge has a composite origin. The classical bulge, the central spheroid that formed rapidly during the galaxy's earliest assembly, may have been supplemented later by a pseudo-bulge, shaped by the secular evolution of the disk, including the redistribution of material by a bar-like structure. This later addition could have introduced younger stars into the bulge, blending populations of different ages and origins. During its formation, the bulge also became a repository for stars from disrupted satellite galaxies. Early in the Milky Way's life, smaller galaxies were frequently drawn into its gravitational field, stripped of their gas and stars, and absorbed into the growing halo and bulge. These accreted stars, often distinguishable by their unique chemical abundances, now coexist with stars born in situ, adding to the diversity of the bulge's stellar population. The central star cluster, an extremely dense concentration of stars within just a few parsecs of the galactic center, formed as part of this process. It contains both ancient and relatively young stars, indicating that star formation has occurred episodically in the central regions for billions of years. The presence of the SMBH at its core does not preclude star formation. Rather, observations suggest that bursts of central star formation can occur when sufficient gas is funneled inward, even in the presence of an active nucleus. By the end of this bulge-forming phase, the Milky Way had acquired a massive central component with a stellar mass amounting to roughly 10 to 20% of the galaxy's total. Its stars were more tightly bound gravitationally than those in the disk, making the bulge more resistant to disruption from subsequent mergers or tidal interactions. The SMBH, now securely anchored at the center, continued to grow more slowly, largely dormant compared to its earlier active periods, but still influencing its surroundings through its gravitational pull. The birth of the galactic bulge was thus not a single, discrete event, but a sequence of interconnected processes: the inward migration and condensation of low angular momentum gas, the rapid formation of dense stellar populations, the accretion-driven growth of the central black hole, and the incorporation of stars from infalling satellites. Together, these processes transform the Milky Way center from a turbulent convergence of inflowing gas into a stable, massive, and chemically evolved spheroid. In the long arc of galactic history, the formation of the bulge marked a turning point. It concentrated a significant fraction of the Milky Way's baryonic mass into a compact region, created one of the densest stellar environments in the galaxy, and established the supermassive black hole that would remain its gravitational anchor. The bulge's stars, old, metal-rich, and tightly bound, are silent witnesses to a period of intense dynamical activity when the young Milky Way was still defining its structure and identity. Today, the bulge still bears the imprint of its origins. Its stars' orbits, metallicities, and ages encode the story of gas inflows, starbursts, and black hole growth. The SMBH at its heart, now known as Sagittarius A*, is quiescent by AGN standards, but remains a reminder that the galaxy's calm present is the result of a far more turbulent and energetic past. The bulge's birth was the culmination of forces acting across multiple scales, from the cosmic web feeding gas into the protogalactic disk to the gravitational pull of a single point-like singularity in the core, all converging to shape the luminous heart of the Milky Way. In the formative stages of the Milky Way's evolution, the young galaxy did not grow in isolation. The universe at the time was crowded with smaller proto-galaxies, dwarf systems containing their own stars, gas, and dark matter halos, drifting through the large-scale cosmic web. Many of these smaller structures were gravitationally bound to the nascent Milky Way, destined to be absorbed through a process known as hierarchical merging. These mergers with small proto-galaxies were not mere side events. They were integral to the assembly of the Milky Way's mass, the enrichment of its stellar populations, and the shaping of its structure and dynamics. The gravitational foundation for these events lay in the dark matter halo of the Milky Way. This halo, massive and extended well beyond the visible galaxy, created a gravitational catchment area that pulled in nearby proto-galaxies. As these dwarfs approached, their orbits decayed due to dynamical friction, an energy loss process in which the moving satellite transferred orbital momentum to the background particles of the halo. Over time, this orbital decay brought the smaller galaxies closer, eventually leading to tidal stripping and full assimilation. The earliest mergers occurred when the Milky Way was still in a relatively primitive state, with a thick, turbulent disk and an actively forming bulge. These early encounters tended to be gas-rich, as the smaller galaxies still retained much of their primordial hydrogen and helium. When they collided with the Milky Way, their gas was compressed by gravitational shocks and ram pressure, often triggering new waves of star formation in both the satellite and the host galaxy. This process contributed to the enrichment of the interstellar medium and added stellar mass across multiple components: the halo, the disk, and even the central bulge. Not all mergers were equal in scale or consequence. The smallest proto-galaxies could be torn apart entirely in the galaxy's outer halo, their stars spread into long, faint stellar streams that wrapped around the Milky Way. These streams, still detectable today, trace the paths of past accretion events, providing direct evidence for the ongoing assembly process. Larger dwarfs, on the other hand, could penetrate deeper into the galaxy before being fully disrupted, depositing stars into the inner halo or even the thick disk. One important consequence of these mergers was the growth and complexity of the stellar halo. The halo's oldest stars often originated in small, metal-poor systems that were accreted during the earliest stages of the galaxy's history. Because these stars formed in environments with slower chemical enrichment than the Milky Way's main body, they tend to have low metallicities and distinct abundance patterns, fingerprints of their extragalactic origin. Over billions of years, the halo became a patchwork of such remnants, each with its own orbital properties and chemical history. Mergers also played a role in shaping the kinematics of the disk. Large enough satellites could gravitationally heat the pre-existing disk, increasing the random velocities of its stars and thickening it vertically. This process is thought to be a major contributor to the formation of the Milky Way's thick disk, an older, puffier stellar component that coexists with the younger, thinner disk. Even smaller satellites could perturb spiral structures or induce temporary asymmetries, creating ripples in the stellar distribution that might persist for hundreds of millions of years. The influx of angular momentum from merging dwarfs could subtly alter the galaxy's rotation curve and internal dynamics. In some cases, mergers may have contributed to the growth of the galactic bar by redistributing material in the inner disk. They also influenced the orientation and shape of the dark matter halo itself, which can respond dynamically to the infall of massive substructures. Chemical evolution, too, was affected by these encounters. Mergers with metal-poor satellites introduced low-metallicity gas into the Milky Way, diluting the chemical composition of the disk and halo gas reservoirs. Conversely, the assimilation of more evolved dwarfs, those that had already experienced several generations of star formation, brought in stars and gas enriched with heavier elements. This exchange of material created a more chemically diverse galaxy, with variations that astronomers can still detect today by analyzing stellar populations in different regions. The merger history of the Milky Way was not constant over time, but occurred in waves, often linked to the galaxy's location within the cosmic web. Periods of relative calm allowed the galaxy to stabilize and form stars in a steady, organized way, while bursts of accretion activity could stir up turbulence, compress gas clouds, and change the rate and distribution of star formation. Some dwarf galaxies likely merged in rapid succession, overlapping in their effects on the host galaxy's structure and dynamics. Among the most significant past mergers was an event often referred to as the Gaia-Sausage-Enceladus (GSE) merger, which occurred several billion years after the initial assembly phase. While not the earliest or smallest, this event dramatically reshaped the inner halo, depositing a large population of stars on elongated, radial orbits. The kinematic and chemical signatures of GSE are still visible in the motions and compositions of halo stars today, underscoring the lasting influence of such accretion events. The process of merging was not entirely destructive to the incoming satellites. In some cases, the cores of dwarf galaxies survive tidal stripping and continue to orbit the Milky Way as bound systems. Examples include the Sagittarius dwarf spheroidal galaxy and the Magellanic Clouds, both of which are still interacting gravitationally with the Milky Way and may eventually be fully assimilated. These ongoing interactions serve as present-day analogs to the countless mergers that occurred in the past, giving astronomers a living laboratory to study the processes that built the galaxy. From a structural standpoint, the cumulative effect of many small mergers was a galaxy with a complex, layered architecture. The stellar halo bears the shredded remnants of long-gone satellites. The thick disk holds stars whose orbits were puffed up by past encounters. The thin disk, continually replenished by cold gas inflows, carries the imprint of merger-triggered star formation in its chemical patterns. The bulge contains a mixture of in situ stars and accreted populations that once orbited far from the galactic center. Even the galaxy's dark matter distribution reflects its merger history. Numerical simulations suggest that accreting subhalos can leave behind persistent density variations in the dark matter halo, which in turn affect the dynamics of visible matter. In some regions, stellar streams trace the locations where tidal forces from the Milky Way stripped stars from satellites, while leaving their dark matter counterparts more diffusely distributed. By the close of the major early merger phase, the Milky Way had roughly assembled the bulk of its mass. Yet the consequences of this accretion era continued to echo through its structure and evolution. The galaxy that emerged from this process was no longer a smooth, uniform disk surrounded by a simple halo. It was a multi-component system enriched by the histories of dozens, if not hundreds, of smaller progenitors. The gravitational absorption of these satellites had thickened its disk, diversified its chemical makeup, expanded its halo, and, in some cases, temporarily altered its overall shape and kinematic balance. The story of the Milky Way's mergers with small proto-galaxies is thus one of gradual but profound transformation. Each dwarf galaxy that fell and brought its own story, a record of star formation, chemical enrichment, and dynamical evolution written in the orbits and compositions of its stars. As they were torn apart and incorporated, their identities blurred into the larger whole, but their influence endured. The modern Milky Way, with its intricate structure and rich diversity of stellar populations, is the direct descendant of this long and complex history of gravitational assimilation. The formation of the Milky Way's halo represents one of the earliest and most fundamental stages in the galaxy's assembly, preceding the establishment of its thin disk and much of its ordered structure. The galactic halo is a vast, roughly spherical component extending far beyond the visible spiral arms, populated by ancient stars, globular clusters, and an invisible but dominant reservoir of dark matter. This halo is not a smooth, uniform shell. Rather, it is a complex, layered structure shaped by both in situ star formation in the early galaxy and the long history of accretion from smaller systems. Its creation involved processes that reached back to the first billion years after the Big Bang and set the gravitational foundation for everything that followed. In the earliest epochs, before the Milky Way had fully condensed into a recognizable spiral galaxy, the surrounding dark matter halo was already in place. This halo, built from the gravitational collapse of initial density fluctuations in the universe, was the seed structure that dictated the future galaxy's mass, size, and gravitational influence. Dark matter, though invisible and non-interacting with light, exerted a powerful gravitational pull, drawing in baryonic matter, gas and dust, from the surrounding cosmic web. It formed a deep potential well, within which the first stars of the Milky Way's progenitor systems were born. The initial stellar halo was assembled from these early populations, many of which formed in smaller protogalactic fragments before coalescing into a single larger system. These stars were typically extremely metal-poor, having formed from nearly pristine gas composed primarily of hydrogen and helium, with only trace amounts of heavier elements produced by the very first generation of stars, population 3. The absence of metals meant that cooling was inefficient, so star formation tended to produce massive, short-lived stars alongside a smaller fraction of low-mass stars, the latter of which could survive for billions of years and are still present in the halo today. Globular clusters, some of the oldest stellar systems in the universe, emerged during this phase. These dense, spherical groups of tens of thousands to millions of stars formed either within the early Milky Way or within smaller dwarf galaxies that were later accreted. Their stars are remarkably uniform in age and composition within each cluster, indicating that they formed in short, intense bursts of star formation. The clusters that originated within the Milky Way's initial collapse tend to orbit close to the galactic center in more isotropic, three-dimensional patterns, while those captured from dwarf galaxies often have more eccentric orbits and chemical signatures distinct from the native population. As the galaxy grew through mergers and accretion, the halo expanded in both size and complexity. Every time a small proto-galaxy or dwarf system was disrupted by the Milky Way's tidal forces, its stars were stripped away and added to the halo. The stellar debris often settled into long tidal streams before dispersing, gradually mixing into the more diffuse halo background. Even now, astronomers can identify many such streams, remnants of past accretion events, arcing through the halo, their coherent motions betraying their common origins. The halo structure is not uniform, but can be broadly divided into two overlapping components: the inner halo and the outer halo. The inner halo, within roughly 15 to 20 kiloparsecs of the galactic center, contains a higher fraction of stars formed in situ during the galaxy's early collapse, as well as material from the most massive early mergers. These stars tend to have moderately low metallicities and exhibit a range of orbital inclinations. The outer halo, extending to distances of 100 kiloparsecs or more, is dominated by stars from accreted dwarf galaxies. These stars are, on average, even more metal-poor, and their orbits are more eccentric, often on radial paths plunging through the galaxy rather than confined to circular orbits. Dark matter plays an essential role in maintaining the halo's structure. Without its gravitational influence, the halo's stars and clusters, moving on a wide variety of orbits, would disperse over cosmic timescales. The dark matter halo's mass far exceeds that of the visible galaxy, creating a gravitational envelope that holds the stellar halo together and stabilizes the orbits of its components. Moreover, the dark matter halo dictates the gravitational potential that influences how tidal streams evolve, how satellites are disrupted, and how globular clusters migrate over time. Globular clusters themselves are valuable tracers of the halo's history. By studying their spatial distribution, ages, and chemical compositions, astronomers can reconstruct the sequence of events that built the halo. Some clusters have orbits and element abundances matching those of known stellar streams, linking them to specific merger events. Others appear to be native to the Milky Way's earliest formation phase, having formed from gas that collapsed directly into the central dark matter potential before any major accretion occurred. The chemical composition of halo stars also encodes a detailed record of the galaxy's growth. Stars formed in small, isolated proto-galaxies tend to have different ratios of alpha elements, such as oxygen, magnesium, and silicon, to iron compared to stars formed in the denser environment of the early Milky Way. This is because the chemical enrichment timescales in dwarfs were slower, allowing more contribution from type I supernovae, which produce iron, before enrichment from massive star supernovae dominated. As a result, the halo contains chemically distinct subpopulations that can be tied to specific progenitor systems. Kinematically, the halo differs markedly from the disk. While disk stars move in roughly circular orbits around the galactic center, halo stars travel on elongated, randomly oriented paths. This velocity dispersion is a natural consequence of the halo's origins, a product of chaotic mergers, tidal stripping, and the lack of a dominant rotational axis during its assembly. The result is a stellar component that is only loosely bound compared to the dense, rotationally supported disk. The outermost regions of the halo blur into the intergalactic medium, and in these extreme outskirts, the density of stars drops to only a few per cubic kiloparsec. Yet even here, the gravitational reach of the Milky Way's dark matter halo dominates the motions of nearby dwarf galaxies, such as the Magellanic Clouds, which orbit within this extended influence. In fact, some of the material in the farthest reaches of the halo may originate from interactions with these satellites, whether from past close passages or ongoing tidal stripping. Over cosmic time, the halo has continued to evolve, albeit slowly compared to the more active disk. New streams from infalling satellites are still being added, while older structures gradually diffuse into the background. Globular clusters experience dynamical friction that can slowly alter their orbits, sometimes drawing them inward toward the bulge. The most ancient stars remain as fossil records, their orbits and compositions preserved for over 12 billion years, offering a direct link to the conditions of the early universe. By the present day, the halo's visible component represents only a small fraction of the Milky Way's total mass, less than 1% in stars, compared to the overwhelming majority in dark matter. Yet its scientific importance far outweighs its mass contribution. The halo holds the clearest evidence of the galaxy's hierarchical growth, the remnants of long-vanished systems, and the signatures of the first stars and star clusters. It is a living archive of the Milky Way's formation history, preserved in 3 dimensions around the galaxy. In essence, the galactic halo is both a relic and a dynamic participant in the Milky Way's life. Born from the collapse of primordial matter into a dark matter well, enriched by the earliest stars, expanded by countless mergers, and stabilized by an invisible halo of dark matter, it forms the cosmic scaffolding upon which the rest of the galaxy was built. The ancient stars and globular clusters within it are silent witnesses to a time when the Milky Way was just one of many small structures forming in a young universe, destined to grow into the majestic spiral galaxy we inhabit today. The establishment of the Milky Way's spiral arms marks a defining moment in its structural evolution, giving the galaxy the graceful, rotating form we recognize today. Although the spiral arms are among the most visually striking features of our galaxy, they are not static, solid structures like the arms of a windmill. Instead, they are dynamic patterns, regions where stars, gas, and dust crowd together temporarily as they orbit the galactic center. The underlying mechanism that produces and maintains these patterns is most often described by the density wave theory, a framework that explains how spiral arms can persist over billions of years without winding up tightly into a featureless disk. In the early stages of the Milky Way's disk development, the distribution of stars and gas was relatively smooth but not perfectly uniform. Small variations in density, caused by gravitational instabilities, tidal interactions with smaller galaxies, or irregularities in the initial gas distribution, began to seed patterns in the disk. Over time, these irregularities amplified into large-scale, wave-like patterns of higher density that rotated through the disk at a speed different from the motion of individual stars. This is the essence of the density wave model. The spiral arms are not made of the same stars over time, but are instead zones where material becomes compressed as it passes through the wave. The process can be compared to a traffic jam on a highway. Cars, like stars and gas clouds, move at varying speeds, but in certain regions, a slowdown occurs, causing vehicles to bunch together temporarily before continuing on. Similarly, stars and gas clouds orbiting the galactic center move into and out of the spiral arms, which act as moving zones of gravitational compression. The arms themselves rotate at a fixed pattern speed, while stars inside the arms often overtake the wave and stars outside lag behind, ensuring a constant flow of material through these denser regions. Gas clouds, being collisional and compressible, respond more strongly to the gravitational concentration in the arms than stars do. As interstellar gas enters a spiral arm, it is compressed, triggering the collapse of molecular clouds and the formation of new stars. This process leads to a distinct separation of stellar populations. The spiral arms are lit by young, massive, short-lived stars, primarily blue and white, while older stars, which are longer-lived and less luminous, are more evenly distributed throughout the disk. The young stars form bright, localized concentrations within the arms, making them visually prominent when viewed in optical light. These young stars, particularly the O and B-type giants, live only a few million years before ending their lives in supernova explosions. Because this lifespan is short compared to the time it takes to orbit the galaxy, they do not travel far from their birthplaces, ensuring that the spiral arms remain highlighted by their brilliance. In contrast, older stars, including sun-like stars and red dwarfs, have lifespans measured in billions of years and can drift far from their birth sites, contributing to the more diffuse stellar background between the arms. The arms also serve as conduits for chemical evolution within the disk. The supernovae from massive stars enrich the surrounding interstellar medium with heavy elements, which are then incorporated into subsequent generations of stars and planets. This enrichment is particularly intense in spiral arms because of their high rates of star formation, leading to localized increases in metallicity over time. As the gas flows through the arms and spreads back into the interarm regions, these metals are dispersed across the disk, gradually raising the overall chemical abundance of the galaxy. Not all spiral arms in the Milky Way are identical in form or origin. Observations suggest that our galaxy has a barred spiral structure, meaning a central elongated bar of stars connects to the spiral arms. This bar is believed to play a role in generating and sustaining the density waves, channeling gas from the outer disk toward the inner regions, where it can feed star formation and possibly the central supermassive black hole. The Milky Way's major arms, such as the Perseus arm, the Sagittarius arm, and the Scutum, Centaurus arm, are complemented by smaller, less prominent segments known as spurs or feathers, which branch off from the main arms and may be transient or shaped by local gravitational influences. The persistence of spiral arms over cosmic timescales has been the subject of much study. Without a mechanism like density waves, the galaxy's differential rotation, the fact that stars closer to the center orbit faster than those farther out, would quickly wind up any spiral pattern, smearing it into a nearly featureless disk in just a few rotations. Density wave theory overcomes this problem by treating the arms as a stable wave pattern that moves at its own constant angular velocity, independent of the exact motions of individual stars. However, this theory does not exclude other processes. Transient arms generated by gravitational instabilities, tidal encounters, or local perturbations can also contribute to the observed structure. The separation of active star-forming regions from older stellar populations is one of the most important observational consequences of spiral arm formation. Infrared images of the Milky Way and other spiral galaxies reveal that older, cooler stars outline the underlying density waves, forming the backbone of the arms. In contrast, ultraviolet and optical observations show the luminous young stars and clusters concentrated along the leading edges of the arms, where the density wave first compresses the gas. Radio observations of molecular lines, such as CO, reveal the dense clouds that precede these star-forming regions, while 21-centimeter hydrogen maps show the distribution of neutral gas across both arms and interarm spaces. This spatial offset between gas clouds, star-forming regions, and older stars is a key piece of evidence supporting the density wave model. In the spiral arms, the sequence typically begins with the compression of gas, followed by star formation, then the appearance of massive young stars, and finally the dispersal of the gas as stellar winds and supernovae blow it apart. The older stars remain, but the brilliant young population fades quickly, leaving the arm's visibility dependent on the continual flow of material through the wave. Over billions of years, the pattern of spiral arms may evolve. Interactions with satellite galaxies, such as the Large and Small Magellanic Clouds, can distort the arms, create asymmetries, and trigger new waves. Likewise, the passage of high-mass clouds or star clusters through the disk can locally amplify or disrupt the arm pattern. These processes mean that while the arm's general structure may be long-lived, their detailed shape and intensity can change on shorter timescales. In the Milky Way today, the spiral arms serve not only as the galaxy's most visually distinctive feature, but also as the primary engine of star formation. They regulate the flow of gas, concentrated into dense regions, and continually recycle material through the birth and death of stars. The alternating regions of bright, young stars and older, dimmer populations embody the dynamic balance of the galaxy's life cycle, ensuring that the disk remains a site of ongoing activity rather than a static, fading remnant. Ultimately, the establishment of the spiral arms transformed the Milky Way from a relatively featureless rotating disk into a grand, structured system with distinct zones of activity and quiescence. The density wave mechanism provides the gravitational framework for these patterns, while the interaction between stars, gas, and dust brings them to life in visible light. The separation of stellar populations along and between the arms preserves a record of this process, one that astronomers can still read today to reconstruct the history and future evolution of our home galaxy. The evolution of the Milky Way's chemical composition is one of the most fundamental processes shaping its structure, star formation history, and capacity to host planets and, eventually, life. In the earliest stages of the galaxy's existence, its gas content was almost entirely composed of hydrogen and helium, with only trace amounts of lithium, the products of Big Bang nucleosynthesis. There were no heavy elements, and thus no dust grains, rocky planets, or complex chemistry. All of these had to be forged within stars and spread back into the interstellar medium over billions of years. The gradual increase in stellar metallicity, the abundance of elements heavier than helium, tells the story of the Milky Way's transformation from a pristine gas cloud into a chemically rich environment. The first step in this transformation began with the short-lived, massive population 3 stars. Formed directly from primordial gas, these stars lacked metals, making them extremely massive and hot. Within a few million years, they ended their lives as supernovae, dispersing the first significant amounts of heavier elements such as carbon, oxygen, silicon, and iron into the interstellar medium. This enrichment allowed subsequent generations of stars, population 2, to form with small but measurable metallicity. These stars could cool more efficiently during their formation, thanks to the presence of metals and dust that radiated away heat, leading to a broader range of stellar masses, including many low-mass stars capable of surviving to the present day. With each successive generation of star formation, the chemical content of the galaxy's gas reservoir increased. This process was cyclical. Gas collapsed to form stars. Stars synthesized new elements in their cores, and supernovae or stellar winds returned these elements to the interstellar medium. Massive stars, ending their lives as Type II supernovae, were especially important for enriching the galaxy with oxygen, magnesium, and other alpha elements. Lower mass stars, particularly asymptotic giant branch (AGB) stars, contributed carbon, nitrogen, and elements produced through slow neutron capture (DS) process. Meanwhile, binary systems involving white dwarfs occasionally produced Type I supernovae, which were key sources of iron and iron peak elements. The metallicity of the Milky Way increased unevenly across different regions of the galaxy. In the dense central bulge and inner disk, star formation was rapid and intense, leading to faster enrichment. Within the first billion years, these regions had already reached metallicities approaching a tenth of the Sun's present value. In contrast, the outer disk and halo, with their slower star formation rates, remained relatively metal-poor for much longer. The halo's oldest stars, many of which are still observable today, exhibit extremely low metallicities, reflecting their origin in an era when the galaxy's chemical reservoir was still primitive. Mergers with smaller galaxies also played a crucial role in the chemical evolution of the Milky Way. Many of these dwarf galaxies were less chemically evolved than the Milky Way at the time of their accretion, bringing in metal-poor stars and gas. These infalling systems often had distinct abundance patterns. For example, lower alpha-to-iron ratios, which are still detectable in their stellar remnants today. The mixing of such material with the Milky Way's own enriched gas added complexity to the galaxy's overall chemical profile. The presence of metals in the interstellar medium had a profound effect on star formation physics. Metal-rich gas cools more efficiently, allowing smaller fragments to form during collapse. This increased the proportion of low and intermediate mass stars compared to the massive stars that dominated the earliest stellar populations. Because low-mass stars live far longer than high-mass ones, this shift in the initial mass function led to a steadily growing population of older stars, contributing to the galaxy's long-term stability. Perhaps the most consequential outcome of increasing metallicity was the emergence of solid dust grains in the interstellar medium. These grains, composed of silicates, carbonaceous compounds, and metal oxides, became the building blocks of rocky planets. Dust also acted as a catalyst for the formation of molecular hydrogen, the primary fuel for star formation, by allowing hydrogen atoms to combine on grain surfaces. Thus, the very same processes that produced planets also reinforced the cycle of star formation. By the time the Milky Way's metallicity reached about half the Sun's present value, conditions were ripe for widespread planetary system formation. Around newly formed stars, disks of gas and dust condensed into planets, moons, asteroids, and comets. In regions of high metallicity, the likelihood of forming rocky planets increased dramatically, since the solid material required to build them was abundant. This is why most known exoplanets discovered to date orbit stars with metallicities comparable to or greater than the Sun's. Metals are a prerequisite for planet formation, and their abundance directly influences the architecture of planetary systems. Chemical enrichment also shaped the potential habitability of these systems. Elements such as carbon, oxygen, nitrogen, phosphorus, and sulfur, all critical for life as we know it, were forged in stars and distributed into the interstellar medium. Water, for example, could not exist in the earliest epochs of the galaxy's history, as it requires oxygen. Only after multiple cycles of star birth and death could molecular clouds contain enough oxygen to form water ice, carbon to form complex organics, and silicon to form solid surfaces. Over billions of years, the metallicity gradient of the Milky Way, the decrease in heavy element abundance from the inner to the outer disk, became well established. Stars born near the galactic center tend to be more metal-rich than those in the outskirts. However, stellar migration, driven by gravitational interactions with spiral arms and the galactic bar, blurred this gradient by moving stars from their birthplaces to new orbits. This migration not only mixed the chemical composition of the disk, but also spread planetary systems of varying metallicities across a wide range of galactic radii. The Sun itself formed about 4.6 billion years ago from a cloud enriched by countless earlier generations of stars. Its metallicity is relatively high, placing it in the upper tier of the Milky Way's stellar population at the time of its birth. This high metallicity was almost certainly a key factor in the formation of Earth and the other terrestrial planets in the solar system. Without the heavy elements forged in ancient supernovae, the solar system could not have contained solid surfaces, oceans, or the complex chemistry that would eventually lead to life. The chemical evolution of the Milky Way continues to this day, though at a slower pace than during its youth. Star formation rates are lower, but every new generation of stars still returns metals to the interstellar medium. Interactions with satellite galaxies, such as the Magellanic Clouds, bring in fresh, often lower metallicity gas that dilutes and redistributes the galaxy's chemical makeup. Over long timescales, this interplay between enrichment and dilution ensures that the Milky Way remains a dynamic, evolving system rather than a closed, static one. In the grand arc of galactic history, the increase in stellar metallicity was not a uniform, steady climb, but a complex, region-dependent process shaped by star formation, stellar evolution, gas inflow, and mergers. Its most far-reaching consequence was the transition from a universe in which only gas giants or barren, icy worlds could form to one in which rocky planets, and potentially life, became common. From the first carbon atoms ejected by population 3 supernovae to the iron in the Earth's core, the chemical evolution of the Milky Way is the thread that links cosmic origins to the conditions that make our own existence possible. Over billions of years, the Milky Way has transitioned from a rapidly evolving, dynamically violent young galaxy into a more mature, stable system. This phase of long-term structural stabilization is the result of a delicate balance between ongoing star formation, the gradual depletion of interstellar gas, and the self-sustaining dynamics that preserve its spiral structure. While the galaxy is still an active, living system, it no longer experiences the extreme rates of star birth or the chaotic structural transformations that characterized its early history. Instead, its present and future are defined by equilibrium, a cosmic balancing act between forces that build new stars and those that remove or redistribute the raw materials required for their formation. The key to this stability lies in the regulation of star formation. In the galaxy's first few billion years, intense starburst phases consumed large quantities of gas, triggered by mergers, gravitational instabilities, and a denser interstellar medium. Over time, however, as the Milky Way settled into its current disk-dominated form, star formation rates declined. Today, the galaxy produces only a few solar masses worth of new stars per year, a modest pace compared to its early epochs. This slower rate ensures that the existing reservoir of cold molecular gas, concentrated primarily in the spiral arms, is not depleted too quickly, extending the galaxy's ability to form stars over tens of billions of years. This moderation is not accidental, but emerges from feedback processes intrinsic to star formation itself. Massive stars inject energy into their surroundings through ultraviolet radiation, stellar winds, and, eventually, supernova explosions. These processes heat and disperse nearby gas clouds, temporarily halting further star formation in their vicinity. On a galactic scale, this feedback creates a self-regulating loop. Too much star formation triggers gas dispersal, which reduces star formation rates, allowing the gas to cool and eventually condense again. The result is a long-term balance that prevents both runaway consumption of gas and a complete shutdown of stellar birth. Gas loss is another factor shaping the Milky Way's stable state. While the galaxy retains much of its mass, it is not a perfectly closed system. Supernova-driven winds can expel some gas into intergalactic space, particularly in the outer regions where gravitational binding is weaker. Additionally, interactions with satellite galaxies and the intergalactic medium can strip or redistribute gas. However, these losses are partially offset by infall of fresh material from the galactic halo or cosmic filaments, as well as gas acquired from merging with smaller galaxies. This constant exchange of material, although much slower than in the past, maintains a steady, if slowly declining, supply of star-forming fuel. Within this equilibrium, the spiral arms of the Milky Way play a crucial role. Contrary to a common misconception, the spiral arms are not fixed structures made of the same stars. Instead, they are regions of enhanced density, the product of spiral density waves that propagate through the galactic disk. As stars and gas orbit the galactic center, they move in and out of these regions. Gas entering a spiral arm experiences compression, which triggers the formation of new stars. This creates the striking visual contrast between the bright, blue, short-lived stars that highlight the arms and the older, redder stars that dominate the interarm regions. The maintenance of the spiral pattern is closely tied to the overall gravitational balance of the disk. The pattern is reinforced by the combined gravitational effects of stars, gas, and dark matter, which together sustain the density waves over cosmic timescales. The galactic bar, a central elongated structure of stars, also contributes by driving gas inward and supporting the spiral arm structure through resonances. As long as the disk retains sufficient mass and rotational stability, the spiral arms can persist for billions of years, even as individual stars constantly move through them. The chemical enrichment of the interstellar medium also influences structural stability. Over time, as metals accumulate in the gas, cooling becomes more efficient, allowing for the formation of dense molecular clouds. This, in turn, ensures that the galaxy retains the ability to form stars in the spiral arms. However, since star formation is now spread out over a much longer timescale, the structural features of the Milky Way are preserved without being disrupted by massive, short-lived bursts of activity. Another stabilizing factor is the reduction in large-scale gravitational disturbances. In its youth, the Milky Way experienced frequent mergers with smaller protogalaxies and interactions with massive companions. Each of these events could warp the disk, trigger intense starbursts, or even change the galaxy's morphology. In the present era, such major mergers are rare. Most gravitational interactions now involve the gradual accretion of much smaller satellite galaxies, which, while still influencing the halo and outer disk, do not significantly disrupt the galaxy's overall structure. This period of relative calm allows the spiral arms, disk, and bulge to evolve in a predictable, gradual manner. The interplay between the bulge, disk, and halo also contributes to stability. The bulge and bar dominate the inner gravitational potential, anchoring the rotation of the disk and funneling gas toward the center, where it can feed the central supermassive black hole or form new stars. The halo, largely composed of dark matter, provides the gravitational framework that keeps the disk bound and resistant to disruptive forces. This combined gravitational architecture allows the galaxy to maintain its shape over extended timescales. Despite this stability, the Milky Way is not static. Over the next few billion years, the spiral arms may slowly evolve, and the star formation rate will continue to decline as the gas supply diminishes. Eventually, without replenishment, the galaxy will enter a red and dead phase, dominated by older, cooler stars. However, this outcome is likely to be delayed by upcoming events such as the predicted merger with the Andromeda Galaxy in about 4 to 5 billion years, which will dramatically reshape the Milky Way structure and reignite bursts of star formation. Until then, the current balance between star formation and gas loss ensures that the Milky Way remains a vibrant, structured spiral galaxy. In summary, the long-term structural stabilization of the Milky Way is a product of self-regulating star formation, moderated gas loss, and the sustained gravitational patterns that preserve its spiral arms. The galaxy has reached a stage where violent transformations are rare, and its defining features, the disk, spiral arms, bulge, and halo, are maintained by a delicate interplay of processes. This stability not only shapes the Milky Way's appearance, but also provides a relatively constant environment in which stars, planets, and potentially life can thrive for billions of years to come. The Milky Way is not an isolated island in space, but part of a small group of interacting galaxies, and among its most prominent companions are the Large and Small Magellanic Clouds, LMC and SMC. These two irregular dwarf galaxies are bound to the Milky Way in a complex gravitational dance, tracing looping orbits that carry them through the outer reaches of our galaxy's halo. Their proximity, mass, and relative motion make them more than passive neighbors. They exert tidal forces, exchange streams of gas, and influence the Milky Way's star formation history. The interaction between the Milky Way and the Magellanic Clouds is a vivid example of how galaxies can shape each other's evolution without undergoing a direct merger. The gravitational connection between the Milky Way and the Magellanic Clouds is ancient, but the exact duration of their mutual relationship remains a topic of ongoing research. Some models suggest that the clouds are long-term satellites that have orbited the Milky Way for billions of years, while others propose that they are relatively recent arrivals, possibly making their first close approach within the past 1 to 2 billion years. Regardless of the exact timeline, the current configuration places the LMC about 160,000 light-years from Earth and the SMC roughly 200,000 light-years away, close enough for their gravitational influence to be significant. One of the most striking results of this gravitational interaction is the creation of large-scale tidal features in the form of gas streams. The most famous of these is the Magellanic Stream, an enormous ribbon of neutral hydrogen gas stretching more than 180 degrees across the sky. This stream is thought to have been pulled from the Magellanic Clouds through tidal stripping and possibly ram pressure stripping as they move through the Milky Way's diffuse halo gas. The Magellanic Stream is not simply a static structure. It represents a major transfer of material into the Milky Way's outer halo. Over time, portions of this gas may cool, condense, and rain down onto the Milky Way's disk, providing fresh fuel for star formation. This process is part of the galaxy's long-term gas budget and could help sustain star formation rates for billions of years. The infall of Magellanic gas has already been implicated in localized enhancements of star formation activity, particularly in the outer disk where incoming material can compress existing clouds and trigger new stellar births. The interaction between the Milky Way and the Magellanic Clouds is not one-sided. The tidal field of the Milky Way also distorts the structure of the LMC and SMC, stretching them and drawing out tidal tails. Moreover, the two clouds are not just satellites of the Milky Way, but also close companions to each other. They are connected by a bridge of stars and gas, the Magellanic Bridge, formed by their mutual gravitational tug. The gravitational interplay between the LMC and SMC likely enhances the stripping of gas from both, making it easier for the Milky Way to acquire their material. The injection of fresh gas from the Magellanic System has important consequences for the Milky Way's star formation rate. While the overall star formation rate of our galaxy is relatively steady, inflows of metal-poor gas can spark localized star bursts by compressing existing interstellar clouds. These inflows may also influence the metallicity distribution of stars in the outer disk, producing younger populations with lower heavy element abundances compared to those in the inner disk. Simulations suggest that the gravitational tides from the LMC, which is by far the more massive of the two clouds, with perhaps 10 to 20% of the Milky Way's mass in dark matter, can also induce subtle distortions in the Milky Way's disk. Observations have revealed warps and ripples in the outer disk that may be explained by past close approaches of the LMC. These structural perturbations can influence the motion of stars and gas, creating density enhancements that act as sites for star formation. In this way, the clouds may indirectly shape not just the amount of star formation in the Milky Way, but also where it occurs. The interaction also affects the dark matter dynamics of the Milky Way. The gravitational pull of the LMC appears to be strong enough to shift the center of mass of the Milky Way LMC system away from the galactic center itself. This displacement can alter the orbits of stars in the halo and the motions of satellite galaxies, possibly affecting the accretion history of the galaxy in subtle but long-term ways. Gas exchange is not the only means by which the Magellanic Clouds influence star formation. Their gravitational effects can amplify the spiral structure of the Milky Way's disk by creating transient density waves. These waves compress gas as they travel through the disk, much like traditional spiral density waves, and may reinforce existing spiral arms or generate temporary new ones. The result is an increase in the efficiency of star formation in certain regions, particularly in the outer spiral arms that are more sensitive to external perturbations. The star formation history of the Magellanic Clouds themselves is also tied to this interaction. As the clouds pass near the Milky Way, tidal forces and ram pressure can compress their gas, triggering bursts of star formation within them. This creates bright, young star clusters and OB associations, some of which may eventually be stripped and added to the Milky Way's stellar halo. Thus, the gravitational relationship between the Milky Way and the clouds not only exchanges gas, but also stars, subtly enriching each other's stellar populations over time. On a longer timescale, the fate of the Magellanic Clouds is likely to be merger with the Milky Way. Dynamical friction, the process by which massive objects lose momentum as they interact with surrounding matter, will gradually draw them closer. The LMC, in particular, is expected to spiral into the Milky Way within the next few billion years, possibly before the much larger collision with the Andromeda Galaxy. When this happens, the clouds will deliver a fresh influx of stars, gas, and dark matter to the Milky Way, potentially igniting a new era of intense star formation similar to earlier epochs in the galaxy's history. Until that eventual merger, the interaction between the Milky Way and the Magellanic Clouds remains a source of dynamism in an otherwise relatively stable galaxy. The tidal forces, gas flows, and structural perturbations they produce serve as reminders that even mature galaxies are not static entities but continue to evolve under the influence of their neighbors. For the Milky Way, the clouds act both as suppliers of vital raw materials for star formation and as agents of gravitational change, ensuring that the galaxy's structure and activity remain subtly, but persistently, in flux. In essence, the relationship between the Milky Way and the Magellanic Clouds is a slow-motion exchange, not a violent collision but a long-lasting gravitational entanglement that shapes both partners. For the Milky Way, this means periodic infusions of gas, modifications to its disk structure, and a gentle but persistent influence on its star formation rate. For the clouds, it means tidal stripping, structural distortion, and eventual absorption. Together, they demonstrate that galactic evolution is as much about ongoing relationships as it is about ancient origins. The Milky Way today is a mature barred spiral galaxy in a relatively stable phase of its evolution, though far from static. It has reached a size, mass, and internal structure that make it one of the more massive galaxies in the local group, second only to the Andromeda Galaxy. Measuring approximately 100,000 to 120,000 light-years in diameter, the Milky Way stellar disk is a vast rotating structure containing hundreds of billions of stars, immense reservoirs of interstellar gas and dust, and intricate spiral arms that continue to host active star formation. Its thickness varies, with the thin disk, rich in younger stars, measuring about 1,000 light-years across vertically, and the thicker disk, composed of older stars, extending several thousand light-years above and below the galactic plane. In terms of mass, the Milky Way's total is estimated at roughly 1 to 1.5 trillion solar masses. Remarkably, only a small fraction of that, less than 10%, is in the form of visible matter such as stars, planets, and gas. The majority is dark matter, an invisible but gravitationally dominant component that forms a roughly spherical halo extending far beyond the visible disk. This dark matter halo shapes the galaxy's gravitational potential, allowing stars in the outermost regions to orbit faster than they would if only visible matter were present. The Milky Way rotates as a vast gravitational system. The Sun, located about 27,000 light-years from the galactic center, orbits at an average speed of around 220 to 240 kilometers per second, completing one full orbit in roughly 225 to 250 million years, a galactic year. Rotation speeds remain relatively flat across much of the disk, a phenomenon explained by the presence of the dark matter halo. This rapid yet balanced rotation ensures the stability of the spiral pattern, with density waves maintaining the graceful arms despite the differential rotation that would otherwise shear them apart. Today's Milky Way is an active, star-forming galaxy. It produces an estimated 1 to 3 solar masses worth of new stars each year. Star formation is concentrated along the spiral arms, particularly in giant molecular clouds where gas densities and pressures are high enough for gravitational collapse to occur. In the inner disk and near the central bar, star formation is somewhat suppressed due to the presence of stronger gravitational forces, higher stellar densities, and, in some regions, the disruptive effects of radiation and stellar winds from massive stars. The central region of the Milky Way is dominated by the galactic bulge, a dense and complex structure extending several thousand light-years across. The bulge contains older stars, intricate dust lanes, and evidence of past dynamical activity, including mergers and instabilities. At its heart lies Sagittarius A*, SGR A*, the Milky Way's supermassive black hole, with a mass of about 4.3 million suns. Though relatively small compared to the largest black holes in the universe, SGR A* exerts an enormous gravitational influence on the central parsecs, governing the orbits of nearby stars and gas clouds. In the present epoch, SGR A* is considered a low-luminosity active galactic nucleus, AGN. Unlike the brilliant quasars of the early universe, it is currently accreting material at a low rate, producing only a faint emission in radio, infrared, and X-ray wavelengths. Observations from telescopes such as the Very Large Telescope, VLT, and the Chandra X-ray Observatory show that SGR A* experiences occasional flares, brief increases in brightness lasting hours, likely caused by sudden infall of clumps of gas or disrupted asteroids. These flares provide a glimpse into the processes occurring near the event horizon, where matter is heated to extreme temperatures before vanishing into the black hole. Despite its current quiet state, there is strong evidence that SGRA* was more active in the past. Observations of giant gamma-ray structures known as the Fermi bubbles, extending tens of thousands of light-years above and below the galactic plane, suggest that an energetic event occurred a few million years ago. This may have been a burst of accretion onto the black hole or a powerful nuclear starburst in the central regions, releasing enormous amounts of energy into the halo. The memory of such events is imprinted in the hot gas, magnetic fields, and cosmic rays still present in the galactic center region. The Milky Way's disk also shows signs of subtle structural evolution in the present day. The spiral arms are maintained by a combination of density waves, triggered star formation, and possibly interactions with nearby satellite galaxies, such as the Magellanic Clouds. The disk is not perfectly flat. It exhibits warps and ripples, particularly in the outer regions. These features may be the result of gravitational interactions with passing dwarf galaxies or dark matter subhalos, as well as the tidal influence of the Large Magellanic Cloud, whose mass is sufficient to perturb the Milky Way's outer halo. Chemical evolution continues across the galaxy. The metallicity of stars, meaning the abundance of elements heavier than helium, varies systematically with location. Stars in the inner disk and bulge tend to have higher metallicities, reflecting many generations of star formation and supernova enrichment. In contrast, the outer disk and halo contain stars with lower metallicities, some of which date back to the earliest epochs of galactic history. This chemical gradient is an important marker of the galaxy's evolutionary processes and gas flow patterns, as inflows of metal-poor gas from the halo and intergalactic medium dilute the metallicity in some regions, while central recycling processes enrich others. From a dynamical standpoint, the Milky Way is still accreting material. Streams of stars and gas, remnants of tidally disrupted dwarf galaxies, wind through the halo, providing direct evidence that our galaxy is still assembling its mass. The Sagittarius dwarf spheroidal galaxy, in particular, is currently being torn apart and absorbed, leaving a vast stellar stream that wraps around the Milky Way. These ongoing accretion events subtly alter the halo's structure and contribute fresh stars and dark matter to the system. On larger cosmic scales, the Milky Way's current motion through space is shaped by its membership in the local group. Alongside the Andromeda Galaxy, M31, the Triangulum Galaxy, M33, and dozens of dwarf galaxies, it orbits the group's common center of mass. The Milky Way and Andromeda are on a collision course, approaching each other at about 110 kilometers per second, with a merger expected in roughly 4 to 5 billion years. This distant event will mark a radical transformation in the Milky Way structure, but for now, the galaxy remains in a phase of gradual evolution, shaped by local interactions and internal processes rather than by major violent events. In summary, the Milky Way's present stage of development is defined by balance. The forces that built it, gravity, rotation, mergers, and accretion, still operate, but at a slower, more measured pace than in its turbulent youth. Star formation continues at a moderate rate, sustained by recycling of interstellar material and modest inflows from the halo. The spiral arms remain vibrant sites of stellar birth. The bulge preserves the record of ancient epochs, and the central black hole serves as a quiet but potent gravitational anchor. While the galaxy's appearance today is that of a stable, mature system, beneath that stability lies constant motion and subtle change. Stars orbit, gas flows, spiral arms shift, and the central black hole occasionally flickers with activity. The Milky Way is not a static monument, but a living system, evolving even now, preparing, slowly and inexorably, for the next great chapter in its history. The Milky Way's future is shaped by both its internal evolution and its place in the larger cosmic environment. While the galaxy appears stable in the present epoch, its long-term trajectory is already set by gravitational interactions within the local group. The most significant event in its foreseeable future is the predicted collision with the Andromeda Galaxy, M31, a vast spiral galaxy approximately 2.5 million light-years away. Both galaxies are bound to each other by gravity and are moving toward one another at a relative velocity of about 110 kilometers per second. Given their separation and speed, this encounter is expected to occur in roughly 4 to 5 billion years. The approach of Andromeda is not a head-on rush in isolation. The local group's gravitational dynamics have been guiding the two galaxies toward each other for billions of years, and both systems are accompanied by their own retinues of smaller satellite galaxies. The collision will therefore involve not just two spirals, but also numerous dwarf companions, streams of stars, and clouds of intergalactic gas. Current simulations suggest that before the cores of the Milky Way and Andromeda merge, the two galaxies will undergo several close passes. Each pass will distort their spiral structures, stretching them into long tidal tails and flinging stars far into intergalactic space. During the first encounter, gravitational tidal forces will warp and twist the disks of both galaxies. Spiral arms will be torn apart and reshaped into elongated streams. Stars in the outer regions will be displaced, and massive clouds of interstellar gas will be compressed, triggering bursts of star formation. These starburst episodes will be short-lived but intense, creating clusters of hot, massive stars that will quickly burn out and end their lives as supernovae. The influx of energy and heavy elements from these explosions will enrich the interstellar medium of the merged system, accelerating chemical evolution. Over the course of 1 to 2 billion years after the first pass, the Milky Way and Andromeda will continue to interact gravitationally. Their mutual attraction will slow their motions, causing them to spiral inward toward one another. By this stage, the original spiral patterns will be largely destroyed, replaced by a chaotic distribution of tidal debris. Gas dynamics will play a crucial role. Colliding gas clouds will lose orbital energy through shocks, sinking toward the combined center of mass and fueling further star formation near the core. This central gas infall may also feed the galaxy's supermassive black holes, Sagittarius A** in the Milky Way, and the even larger black hole at Andromeda's center, possibly triggering an active galactic nucleus phase. When the galactic cores finally merge, the result will likely be a single, massive elliptical galaxy often referred to as Milkomeda or Milkdromeda in astrophysical literature. The transformation from two rotating spiral disks into a rounded, dispersion-dominated system will be driven by the violent relaxation process, in which the gravitational potential changes rapidly and redistributes stellar orbits into random, three-dimensional motions. Much of the ordered rotation will be lost, replaced by a slower, more spheroidal stellar distribution. The merger will have profound effects on the structure and stellar population of the resulting galaxy. The star formation rate will peak during the earlier merger phases and then decline sharply as the available cold gas is consumed or heated. Over the following billions of years, the new galaxy will fade, its population dominated by long-lived, low-mass stars. The remnants of the Milky Way's and Andromeda's spiral arms will be indistinguishable, their histories preserved only in the orbital motions of stars and streams within the halo. For the solar system, the story is both dramatic in scale and surprisingly calm locally. The vast distances between stars mean that the probability of a direct collision between the Sun and another star is extremely low, even during the most chaotic merger phases. However, the Sun's orbit within the Milky Way will be altered. Currently, the Sun orbits about 27,000 light-years from the galactic center. The gravitational disturbances of the merger will likely scatter it onto a new trajectory, possibly moving it farther from the center or placing it on a more eccentric orbit within the merged galaxy. By the time the merger begins in earnest, the Sun will be approaching the end of its life. In about 5 billion years, it is expected to exhaust the hydrogen in its core and expand into a red giant, engulfing the inner planets, including possibly Earth, before shedding its outer layers and leaving behind a white dwarf. Thus, for the solar system, the changes in galactic structure may be of little consequence compared to the Sun's own transformation. If Earth survives the red giant phase, the altered galactic environment could affect its night sky dramatically. Instead of the familiar band of the Milky Way, the sky would be filled with bright knots and arcs of stars from the colliding galaxies, creating a celestial panorama unlike anything seen in human history. After the cores merge, the supermassive black holes of the Milky Way and Andromeda will eventually spiral toward each other due to dynamical friction, emitting gravitational waves as they approach coalescence. The final merger of the two black holes will release an enormous burst of gravitational energy, detectable across the universe with future observatories. The merged black hole will sit at the heart of the new galaxy, its mass potentially reaching tens of millions of solar masses, influencing the orbits of nearby stars and the dynamics of any remaining central gas. Long after the merger has settled into a stable elliptical form, the galaxy's future will continue to evolve on cosmic timescales. Star formation will slow to a trickle as cold gas is exhausted, and the galaxy will gradually redden as hot, young stars disappear and only older, cooler stars remain. In the far future, gravitational interactions with other members of the local group, by then likely merged into a single gravitationally bound system, could lead to further mergers, slowly building even larger structures. On truly vast timescales, hundreds of billions to trillions of years, the fate of the galaxy will be determined by the expansion of the universe and the eventual depletion of its stars. If dark energy continues to accelerate cosmic expansion, Andromeda will eventually become isolated from all other galaxies as the observable universe shrinks. Its stars will age, cool, and die, leaving behind a dark galaxy populated by stellar remnants, cold planets, and black holes. The once bright arcs of spiral arms will be a distant memory, their light long faded into the infrared and radio domains. Thus, the future of the Milky Way is a journey from ordered spiral beauty to the grand, if chaotic, drama of a major galactic merger, followed by a long decline into cosmic quiet. For billions of years to come, it will remain a dynamic system, reshaping itself through gravity, star formation, and interaction, until the processes that sustain its luminous structures fade away. In the grand narrative of the universe, the Milky Way's future is both a continuation of the forces that built it and a reminder that even the most majestic cosmic structures are subject to change, transformation, and eventual fading into the vast darkness of deep time. Good night.